This is a focus on functions. It's actually after section 8.4 in your book. But it's about types of discontinuity or points of discontinuity. Rational functions can have a couple of different things. Discontinuities are breaks in the graph. That's all they are. We have vertical asymptotes. Those we've talked about. Okay, vertical asymptotes, those are considered non-removable. They're also considered infinite discontinuities, and they come from factors that don't cancel. Okay, you'll see what I mean when we do a couple of examples. They're infinite because they are lines that go on and on forever in both directions. They're non-removable because they don't cancel. That kind of thing. That'll help you remember what those types are. Then we also have, we could have a hole in the graph. Okay? A hole is just a point that's not there. It's a point in the graph that does not exist. So it's called point discontinuity. It is removable. Why is it removable? Because it's just a little point. I could put a point right back in it and take it away. Also, another thing that we can consider removable is it comes from a factor that cancels. Okay, the factors cancel, their factors are gone, so the discontinuity can be considered removable that way. Okay. Alright, let's look at an example. Here is an example. We've got y equals x squared minus 16 over x plus 4. We need to get into the habit of factoring everything that can factor. This is the difference of two perfect squares. It's going to factor to x plus 4, x minus 4, and that's going to be over x plus 4. Okay? Well, we have common factors, and anytime we have a numerator and a denominator with a common factor, they can cancel. So what the graph of this function is going to look like, it's going to look like the line y equals x minus 4. So this graph looks just like this line, but there is a hole in the graph where x equals, because we have this point of discontinuity, x plus 4 is in the denominator of our original function. So therefore, x cannot equal negative 4. So we have a point of discontinuity there. Is it an asymptote or is it a hole? In this case, it is a hole because the factors canceled. So it's a hole in the graph. Now, where exactly in the graph is that hole? I'm going to plug in negative 4 into my simplified version. Plug in negative 4. Okay, so where exactly is the hole? Okay, we'll plug in negative 4 into your simplified version. So y equals negative 4 minus 4 equals negative 8. So the point, negative 4, negative 8, does not exist in this graph. So that's the hole. The point, negative 4, negative 8, does not exist in this graph. So when we were to graph it, I'm making my scale a little funky here. We'll go with 4, 8. So when we were to graph this line, x minus 4, so negative 4 is my y-intercept. My slope is 1. Since my units are by 2, if I go up 2 over 2, that's still just a slope of 1. Up 2 over 2. And down 2, back 2. Down 2, back 2. This is where my hole is. Negative 4, negative 8. Let me make it look a little more linear. Okay. In the graphing calculator, if you plug this in to your graphing calculator, it will show up as this line, but you won't see an empty space there because the graphing calculators, we can't get close enough to that little space to make it a blank spot in the graph. Because to be honest with you, Negative 3.9999999 is part of the graph, just like negative 4.000000001 is part of the graph, but only where it's exactly negative 4 is that point not there. Okay, so the graph doesn't have, the graphing calculators or any graphing technology has the capability to show us that one little teeny tiny spot that's not there. Okay. All right. Can you have holes and asymptotes? Yes, of course. And here is one where we might see both. Okay. Start by factoring everything. Okay. Difference of two perfect squares. X plus 3, x minus 3. The bottom here is going to factor to x minus 3, x plus 1. Okay, before we cancel, let's look at the denominator and decide about your points of discontinuity. Okay, what can x not equal? Well, x cannot equal 3, and x cannot equal negative 1. Okay, these two are points of discontinuity in the graph. So, now we cancel. The x minus 3's will cancel. So, f of x is going to look like the graph x plus 3 over x plus 1. Okay? This is what the graph will look like. But, there's going to be a hole, a hole, when x equals 3. So, to find out exactly where the hole is, plug in 3. 3 plus 3 is 6. Over 3 plus 1 is 4. So the hole is going to be at 3 and 3/2, or 3, 1.5. So there's the hole. This is going to be an asymptote, a vertical asymptote, where x equals negative 1. How about a horizontal asymptote? Looking at the simplified version, the horizontal asymptote, the degrees are the same, so the leading coefficients are 1 and 1. The horizontal asymptote is y equals 1. Okay? So if we were to graph this, there's your vertical asymptote. There's your horizontal asymptote. At 3, 1.5, we have a hole. We're going to have curves like this and this. This type of a graph is called a hyperbola. And it's got two branches. We've got a branch here and here, and they're actually mirror images of each other. If you were to fold them along that line, they would line up with each other. The difference here is we have a hole here. There is no hole over here. Okay? So, we can have asymptotes and holes in the same graph.